اوكي، بسم الله الرحمن الرحيم والصلاة والسلام على أشرف المرسلين سيدنا محمد وعلى آله وصحبه أجمعين. السلام عليكم everyone. What we done so far in topic number 3 is that we looked at we already from topic number 2 we looked at the kinematics and the dynamics of one rigid body just floating in the air. And then when we started to look into fixed base manipulators, we said that we want to have multiple rigid bodies connected together through what we call joints. So, and these joints, we represented them, we represented them by this idea of displacement subgroups. And then we looked at constrained spaces where you say, okay, that the twist, okay, of the parent and the child, they are related together. They're not just free to do whatever they want. They're constrained by the fact of this joint. What we're going to be doing today, inshallah, is that we're going to be looking at the dynamics. We only discussed the kinematics so far of these joints and how they link the two bodies together. Now we're going to be looking at the dynamics. And when we say dynamics, it means, okay, it means we're going to be including the forces and the torques, which in the end, on the rigid bodies, they are the wrenches. And we're going to be seeing how everything in the end connects together so that we can reach the equations of motion for a fixed base manipulator. So today's lecture is a little bit dense, okay? I don't know how dense you perceived last lecture, but in my opinion, this is denser from last time, okay? So hopefully we'll be able to finish it, okay? So first, this is a recap of what we discussed, is that we said the way we're going to be doing the forward kinematics and the differential kinematics is by what's known as the exponential map. And the exponential map of SE3, in the end, if you have a parent and a child, two bodies together connected by a joint, then the relative twist is simply given by a map, okay? It's just a constant unit twist multiplied by the QC dot, where QC dot is the angular velocity, okay, or the generalized velocity of the joint. And we have here the homogeneous transformation matrix as a function of Q. The integral of the Q dot is given either in this form or in that form, depending on whether you represent this unit twist in the parent or in the child frame. And this exponential map, it has a closed form expression that you can program and you can use as you wish. And then we looked at how does this unit twist looks like, or the screw axis. So this is the notation we use, the screw axis. If we have a prismatic joint, is simply given by zeros on the top and the axis around which you're translating. And if you have a revolute joint, it was a little bit more complicated. We have the axis of revolution on the top, and on the bottom we have this cross product between the axis of revolution at any point on the body. Any point on this revolution axis. And then we said that the forward kinematics is a map that will take all of the Qs that you have for each of the links, for each of the joints that you have. And in the end, it will tell you what the pose of the end effector is with respect to the base of the robot. And the base of the robot here is not moving, and thus the name fixed base manipulators. And we said that the product of exponential formula will allow us, given this home configuration pose, and all of these screw axes represented in the base frame at the home configuration. And if you have the configuration the current configuration that you want to calculate, you just plug in this product of exponentials formula, and it will tell you, it will solve for you the forward kinematics. So it's just one line, okay, provided that you have this piece of information. And the differential kinematics, again, is a map from Q dot to H dot, but we know that H dot is related to the twist of the end effector with respect to the base. And this map is a map from Rn to R6, which means it's a 6 by n matrix. And this 6 by n matrix was given by the Jacobian, the spatial Jacobian of the end effector. And we showed last time that it has, so it's a 6 by n matrix, which means it has n vectors, n column vectors. Okay? Each one of them is a screw axis, and each one of these column vectors is given by an expression that looks like this. This is a generic form, and if you want I equal to 1, you plug in, for example, I equal to 1 was just, the first column was simply just S1 with respect to 0 expressed in 0. If you have the J2, it will be only one, it will be that joint with one screw axis multiplied by one screw axis. And if you have the J equal 3, you're going to have 2. If you have J equal 4, you're going to have 3 of these terms, and so on and so forth. So you can just plug it in. It's very easy, okay, just to program this, and in the end, just call it with whatever, okay, I that you have. And I, of course, will be from 2 to n in general. So this was it. This was the differential kinematics and the forward kinematics, something very systematic, something that you can program. And inshallah, next time I'm going to show you how you can program it and how easy it is just from this, okay, from all of the time that we invested in building up the math that we require, the implementation part becomes very simple, okay. Today, inshallah, we're going to be seeing how we can use this, all of this information. So the bottom line that you see what we have here by solving the forward and differential kinematics, the only input to this process, to these equations, is the home pose of the end effector and all of the screw axes that define the joints. And there was something very important here that we said, in order to solve the forward and differential kinematics, we don't need to put any intermediate frames. Okay, we just need the end effector frame and the base frame, and that's it. And the output of this is the pose of the end effector at any configuration Q. So you say what the Q's are, and you see what the end effector looks like. And you have also the spatial Jacobian, the spatial end effector Jacobian. And if you multiply this, as we seen last time, by the adjoint from of the H from 0 to E, we get the JE0E. Okay, and this JE0E was the end effector body Jacobian. So it's the same as this. Okay, it's the same information. There's nothing different. Both are equivalent. The only difference is that the columns of this matrix, they're represented in the zero frame, while the columns of this one are all represented in the effector frame. Okay, and this is a very important object. You're going to be seeing it. It will play a big role when we talk about the dynamics, and it plays a role when you talk about something called manipulability. It takes a very important role when you want to do inverse kinematics. It's a very important role when you want to look at singularities and so on and so forth. So it's a really very important object. If you really want to do real robotics, this is something that you need to study in a lot of details. What we did for the end effector Jacobian, we can repeat for any link. Okay, and it's very easy actually to do it. So you remember last time we said that even though we did not introduce any intermediate frames, in case you want, okay, to have the pose of any intermediate body, you just assign to it a frame, okay, frame I, and the pose of the frame I with respect to the base will be simply a function of all of the joints from 1 to I, and it will be a function like this. Okay, that's it. So it was as easy as that. We did not show what happens if you want to get the twist of the I frame with respect to the zero frame expressed in the I frame. Okay? And this is a very important object that we're going to be needing a lot today. So let's see what happens. Okay? So this is the exact same steps that we did last time. I'll just go very quickly over them because you just need to repeat what we did for the E case. So here, what we did last time, if you remember, this was the starting point when we wanted to discuss when we wanted to derive the Jacobian. We started by saying that the end effector twist with respect to the zero frame expressed in the zero frame is simply 1 with respect to 0 plus 2 with respect to 1 plus 3 with respect to 2 up to n minus 1 with respect to n. And we also had like an E with respect to n, but we said this is 0 because they are both connected to the same body. If you want to have the ith link, okay, the twist of it, it's simply you go from 1 to 0, 2 to 1, up to I minus 1, and everything else afterwards becomes 0. You remember there was a question last time about what happens if all of this thing, if all of the joints here, they are fixed, and you start to moving these joints. What happens to this I frame? It doesn't move at all, right? Exactly, it remains fixed, which means that the twist of it is 0. So in other words, the twist of this frame with respect to this, okay, with respect to that frame, it does not depend at all on all of the joints that come after I. Okay, from I till the end effect. So that's exactly what this says. If you do the same, which means actually that if I repeat the exactly same steps that we did before, you're going to find that we're going to have one column corresponding to this twist, another column corresponding to that twist, up to the ith column. And from the ith column to the nth one, so from I plus 1 up to n, I just have zeros. Okay. So in the end, if I want to write the twist of the ith frame with respect to the 0 expressed in 0, I can define a new Jacobian that will have exactly this, the first I columns of the end effector one and embedded with zeros in the end. And this is, you can multiply by Q dot to get the 3. Easy? Okay, so it's very easy. I just filled in from I plus 1 up to n with zeros. That's it. And if you multiply this matrix by, from the beginning, from the left, from adjoint of h from 0 to I, in the end, we're going to have the twist of I with respect to 0 expressed in I. So you see now we have a matrix that's multiplied by q dot that will give us the twist of the ith body, okay, of the ith link on the robot. And it's this matrix, okay, you can just pre-program and you can store it and you can use it whenever you want. So this matrix, okay, we're going to be denoting it by Ji0I, and we're going to be calling it the geometric body Jacobian of link I. Okay? Anything new? Just a simple, okay, extension of what we discussed so far. Make sense? Easy? Okay. So that's the first thing we want to do. Let me show you something very powerful of what we just did. You remember what does this look like? What does this represent on the board? Of what? No? What is this the kinetic energy of? What is this the kinetic energy of? Which rigid body? Take a look carefully. All the bodies for the whole robot. Okay, all the joints are just moving around. Okay, so each link is just doing something, and in the end, if you take the summation of, so the inside of the, you see there's a summation here from I equal 1 to n, and each one of these component is simply the kinetic energy of the ith body. Okay.
The body is consistent of ice frames.
Exactly. So what usually, so the convention that we do is that we say that every body that we have, we're going to attach to it a body fixed frame. We're going to be calling, if we have the ith body, we're going to be attaching to it the ith frame. So frame I is attached to link I in the robot. Okay. Exactly. Yes.
You're expressing each kinetic energy in its own body's frame?
Yes, we're doing this such that the generalized inertia that you see here, when we represent it in the I frame, what do we get? What was the important part about doing this?
Yes.
No, we're not assuming it's at the center of the mass. We did not make this assumption. The question was, when we represent the generalized inertia of the ith body in the ith frame, what happens to the I? It's a constant. It becomes just a constant matrix, a constant 6 by 6 matrix. It had J on the top, it had mass multiplied by the identity, and there on the of the diagonal terms there was the tilde form of the skew symmetric. Of the center of mass location. So yeah, it's a fixed frame to the body, exactly. So the ith frame is fixed to the ith body. If the ith body is moving, the ith frame will move with it. Okay, and it's not necessary that we place it at the center of mass. We can, but not necessary. If you place it at the center of mass, you know how the I looks like. Okay, it just becomes simplified. So in the end, what you see here is the kinetic energy of the ith body. If you sum them all, you get the kinetic energy of the whole robot. Make sense? Okay. We just said that the VI0 with respect to I can be written in terms of this Jacobian as the following. Take a look at this expression and see whether it makes sense or not. Okay, if you know how to go from here to here, you're good to go. We just remove the V with the J multiplied by the Q dot. And here, this was supposed to be V transpose. If V is equal to J multiplied by Q dot, then V transpose would be Q dot multiplied by J transpose. Make sense? Everything that's inside of here, okay, the Q dot, by the way, does not depend on I, right? So actually, we can take it out of the summation, and we're going to have here inside, we're going to have a summation of these terms that depend on the I. If we take all of this stuff, can you calculate or can you check what's the dimension of this matrix that we're going to get? Do you remember what was the dimension of the I? 6 by 6. What's the dimension of the J? 6 by n. It was 6 by n. So this is 6 by 6. This is 6 by n. And here it is n by 6. What is the result if you multiply these? It's an n by n matrix. What do we call this? We call it the mass matrix. Okay, so what you see inside of here, the kinetic energy of the full robot, which consists of n links, okay, a fixed base robot that consists of n links doing all of the stuff crazy, we can in the end is given by half q transpose multiplied by m of q multiplied by q dot. So half q dot transpose m of q dot, where m of q is given by this summation. Is it easy to program?
What will be inside the mass matrix?
Very good. Whatever comes out of here.
Give us the mass matrix as a given.
Yeah.
It's an n by n matrix.
That's right.
What will be inside it? Like, how can we express what's inside this matrix?
So what you see from here is that, first of all, if you multiply the I itself, let's take the generalized inertia of the ith body. What piece of information is there? Yeah. The generalized inertia. What kind of information, what kind of numbers you will find inside? The moment of inertia of the ith body. What else? The mass of the ith body. The location of the center of the mass in the ith frame. The location of the center of mass in the ith frame. That's the piece of information that you find here. What about the J? What kind of information do you find there? We need to revise a little bit what it was. So the J, okay, was a matrix full of columns, okay? And each one of these columns, if you go back to it, was given by this. It had inside of it the Q's, so it's a function of the Q's, but what else? The screw axis, and only that. So in the end, inside of the J, there are just screw axes. What was inside of the screw axis? Do you remember what the example we did in the last lecture? The axes, the directions of the joints, and some distances, which in the end are just kinematic parameters. You know, how tall is the link, right? It had, you know, length and if there is an offset and so on and so forth. So in the end, you just find distances that and directions. That's it. So what's inside of this? So now if you go back to this, what's inside of the mass matrix? You find the inertia and also the kinematic parameters, the distances, the lengths inside of it. Okay.
Information related to the matter of the body.
Exactly. Absolutely. It has, so what Asha said is that it has all of the pieces of information related to the matter of the body. Okay. And thus, you see, we only talked about the mass matrix. Now when we're starting to talk about the dynamics. Okay. If you don't have dynamics, if you have kinematics, you don't talk about inertia. Once you start talking about the dynamics, you start to talk about the inertia. Make sense? So far, so good? Okay. So let's look at something. So we're going to just collect a number of pieces before we go to the dynamics part. Okay, so this is the first piece that we looked at, the ith link Jacobian. Now let's look at something very important. So these are the two equations we discussed so far. And we said that when we have a joint connecting two bodies, a parent and a child, that the relative twist will be given by q dot multiplied by the 6 by 1 vector, which we call the screw axis. This is a constant that defines in the end, okay, what axis are we rotating around and like the distance of how it's placed in the child and parent thing. While the link body twist, okay, is again another transformation from a q dot to a twist. Okay, but inside of here is the J matrix, and inside of this J matrix was also columns that correspond to screw axes, but they were just transformed by the adjoint. So in the end, they are just screw axes, but represented in different frames. Now let's look at, this is only the velocities. When you have a joint, what comes to your mind? So what is missing here before we go to the dynamics? So this is only kinematics, right? You have velocities, how they are related to each other. We need the forces. In general, what will be the dual to a twist? A wrench. What about the dual to a q dot? So what is the q dot? Do you remember what is the q dot? What was the q dot itself? The velocity of the joint. It can be revolute or prismatic. It doesn't matter. Okay, so we're talking about in generally. Even though it's just it's a prismatic, it's a revolute joint in the picture, but this also holds for if you have a prismatic joint. This is just linear velocity or angular velocity. The dual. What's the dimension of this q dot? C. Q dot C. One dimension. It's just the angular velocity of the one joint that we're talking about. Okay. So here, the dual of the angular velocity is what? The torque, exactly, of the motor that's turning this on. Okay. If you have here, this is an active joint, which means that you're actuating it by some motor, okay, or whatever actuator that you're using, then we're going to have here a torque that's dual to the q dot. And inside of these two bodies, there is something that's preventing them from going away to each other. Usually, if you had any course on mechanics, you'll know that this is usually called the constrained forces or the constrained torques. If you combine both, you get the constrained wrench. Okay. So you see here, there is a duality here between the twist and the wrench, but also a duality between the torque and the angular velocity of the joint, or the velocity of the joint in general. Even though this can be prismatic or or revolute, we're just going to be calling it tau in both cases. Okay, and it will be a force or a torque depending on whether you have a prismatic or a revolute joint. If you multiply tau by q dot, okay, you'll find that it's equivalent to the transpose of the wrench multiplied by the v. Okay, it's very easy to check this, by the way. Okay, so what was the v? It's s multiplied by q dot. If you take the transpose, so you have wrench transpose multiplied by s. If you transpose both of them, you're going to get s transpose multiplied by the wrench, which in the end is the tau. It's very easy to check. It's just one line. What does this equation tell you? The power, so this relative, okay, twist between the two, okay, between the two bodies, in the end is equal to the power supplied by the actuator. Okay? So the power supplied by the actuator is simply, okay, equivalent to this wrench, okay, times this velocity. What did we call this product before? Is it an inner product? Why? Two different spaces. What do you remember? What did we call this pairing or this product? It had a special name. No. You're almost there. It was called a dual product. It's different from the inner product. Okay, an inner product is between two velocities, two vectors. Okay, in the same space. But now we have a vector and a covector. So when we take something like the dot product between them, it's actually called the duality product between. The same also here between the tau and the q dot. But actually, the tau and the q dot here are just scalars, so you don't care about them. Can we do the yes? It will be clear, hopefully, in the coming slides. Leave that question until the coming slide. I'll show you something similar to it. Maybe it makes more sense. If you have here on the ith body, you have an external wrench acting on it. Does this correspond to some torques? Imagine, for example, that you come at the ith link and you press on it. Okay, you push on it with your hand. And you want to balance this. Okay. Is this equivalent to some torques that you apply from the actuator to balance it? Are you sure? So, for example, if you come at the end effector and you start pulling it, what will happen? All of the robot will be affected, exactly. So there will be a torque applied on all of the robot. That's the whole idea, right? So you see, if you apply something at the ith link or at the end effector, okay, what will happen is that you're going to have an equivalent torque that corresponding to that. Okay, so this expression will come later on. You'll see it's very important. But the key idea that I want to show you here is that the map that will go from the wrench to the twist is actually the transpose of the Jacobian that maps the q dot to the body twist. And if you look at if you couple these equations together, you'll find exactly the same expression, that the power, okay, corresponding to the wrench applied at the ith link, or where I here can be the end effector. Okay. So, or any other link. So the wrench applied at the at the ith link, the power with the, if you multiply this, the wrench multiplied by the body twist, in the end you get the duality product between the torques corresponding to this force, to this external source, and multiplied by the q dot.
External, like the motor.
Tau external, if it's the motor, then you're talking about this case, the actuation case.
The same.
Here, it could be something external. So, for example, like gravity, like if you have an interaction, for example, if this robot is drawing on the table, and when you're pressing on the table, there's a reaction wrench applied to the body, and this reaction wrench, what's the corresponding torque to it? You multiply by the J transpose, you get this reaction torque. Yes. Here, this is a map from Q dot to V. So these are all of the Qs. So this is actually what you see here on this side is actually a generalization of this. This is only one Q, while these are all of the Qs of the robot. So that's it. And if you remember what was inside of the J, they were actually screws. All of the screws represented in the ith frame. Okay? Yes, sir. Yeah.
Force of one on the other with the external force?
Yes, exactly. Anything external to the robot itself. Yes.
But the motor also could be something external.
The motor we don't consider external. That's why you see this part. The motor, okay, is actually something that's at the joint level is complementary to, it's only along the screw axis, because the screw axis is exactly the motion you're allowed to do. You remember this is an S, right? It's 6 numbers. A lot of them were zeros, right? The places where are zero means the joint is actually preventing the both bodies from moving relative to each other. Intuitively, it's this picture. For example, take these two bodies. Am I allowed to move the two bodies like this? Why? It's constrained, which means that you cannot have any actuation force in this direction. The same actually in all of the three forces. All of the translational degrees of freedom are prevented by the joints. You remember what we said about the joint, that if it allows B degrees of freedom, it constrains 6 minus B? That's exactly here, the idea.
But sometimes when the external force exceeds the actuator, sometimes it can break the constraints.
So here, everything is within the realm that, within the mechanical limits. We're not breaking, we're not saying that. So we're not saying that, for example, there's a force that's applied very strong that it will actually break, the bodies. No, it's now you're actually breaking the robot itself. We're not there. Okay.
Viscous force are also external.
Viscous, what viscous?
Viscous.
Friction in the joints. There'll be something like this. Here. This is similar to what the friction. It's in the direction of allowed motion. You represent it like this. Exactly. At the joints. Here, this is general. What's inside of the J here, so the J here is a map from the Q dot to the V, which in the end are the tau external and the V. This is a linear map, and there's something, so a linear map is between two vector spaces, right? So this is a linear map between two vector spaces. If you really want to know what will happen from when mapping from here to here, you need to analyze what's known as the kernel and the range space of this J. And you start to go into a very, and all of the stuff that I mentioned about the maneuverability and the manipulability of the robot and so on and so forth. So there's a lot of stuff on how well, so when you're designing the robot, how well will it be able to do the task? Not just can it reach the point. So you need to just stop thinking about, the robot will move from point A to point B. But what if it reaches this point and we start to want to make it an action? I'll give you an example what I mean by that. So can I push a force on my hand here? Right? I can push a force, right? If my hand is like this and you put for me a surface, can I push on the hand? On the It's not singularity, actually. What you're talking about here is that you're no longer, because of the J here, you're no longer able to apply any forces because you've reached the maximum. So the manipulability of how much you can apply forces actually depends on where you are. Okay, and it depends on even in between. Okay? And this is very important if you really want to design, a robot, or you want to look at the forces that I'm applying. Okay, so again, this is part of the discussion I told you. This is very deep stuff. You really need to analyze a lot what the J looks like and how it affects the robot's performance and so on and so forth. Yes.
Allows the motion only along the screw axis. Will it be considered in the screw axis or the external forces?
So again, the question was, if the external wrench is applied to the ith body along the screw axis, then you're gonna get, in the end, you're only exciting, I think, this body.
Dial down to that specific.
I think so. Yeah, I think so. Exactly. It's like you're looking at the columns of this and you're exciting one of the columns only. Exactly. Something like this. Yeah.
What about the passive joints? Something.
Excellent question. What about passive joints? You have this equation equal to 0. That's it. So it still works. If you have passive joints, then we just have this equation is equal to 0. You're not applying any wrench. Here, this is on the whole robot. If the whole robot is passive, it's not called a robot, actually. It's just, some links connected to each other. Okay. So now let's look at, again, so now these are the two pieces we need so far. The first one is the link geometric Jacobian. The second one is the twist and the wrench duality. Now let's look at one extra piece, which is now what happens to the dynamics of the parent and the child together connected by the joint. This is the kinematics. This is a summary of the kinematics we discussed so far. We said that the relative pose between the two bodies is given by the exponential map. Okay? And here we represent it in the parent frame. You can also do it in the child frame, but you just do it in the parent. And the relative twist is simply given by the S multiplied by the Q dot. Now, this is a very easy formula to show that if the child twist relative to some fixed frame is equal to the parent twist relative to the fixed frame plus the child with respect to the parent. Make sense? So this one, how it's moving, is this. So this one with respect to that one is equal to, so the twist of this with respect to, of C with respect to S is equal to P with respect to S plus C with respect to P. You see how these two, they match together. So you're left only with C with respect to S like this. And they're all expressed in the same frame, right? Make sense? If we choose here to represent this in the C frame, so this in the C frame is equal to that in the C frame plus this in the C frame. If this is represented in the C frame, we said that this is equivalent to the screw axis multiplied by Q dot. And if this is represented in the C frame, we can relate it to the twist of P with respect to S expressed in the P frame by the adjoint from the P to the C. If you know how to go from this equation to that equation, you're in a good shape. Okay? Make sense? So that's on the kinematic. This is just all of the kinematics. What about the dynamic stuff? So you're all familiar with the free body diagram? Okay. What happens when we do a free body diagram? You talk about the reaction forces, exactly. You just look at, there's the two bodies, okay? And the first body is acting on the second body with some force. The second body is acting on the first with the force. And now here, this could be in general, a force and a torque, which means a wrench. So we're going to be introducing here two wrenches. They're actually in the end one wrench, by the way. So we're going to be denote W, C down, P up to be the reaction wrench of the child on the parent, of C on P, expressed in any frame, doesn't matter. And we have P with respect to C, expressed in C, in the star, in any frame. What's the relation between these two? Equality with a minus sign. What is this called? Who invented this? Who discovered this? Or what? Newton's third law, exactly. Newton's third law is that for every action, there's a opposite and equal reaction. That's it. But just written in wrenches. Make sense? And the body alone, and the parent alone, and the child alone, each one of them has its own dynamic equation. Do you remember this equation, the Euler-Poincare? So we have the differential equation on the parent twist. We have a differential equation on the child twist. And the only forces that appear here are the child acting on the parent, and here the parent acting on the child. There is a catch that this equation has to be all represented in the C frame, and all of this equation has to be represented in the P frame. So you know that C with respect to P expressed in P as the wrench is minus of P acting on C expressed in P. And if I want to represent this in the C frame, then I need to multiply by the transpose, okay, from P to C. Make sense? Easy? Okay. Another thing, which is exactly what we just mentioned now, if we multiply the screw axis by this reaction wrench, you're going to get any actuator torques that you have between these two bodies. And if there are no actuator torques, what do you get? You got zero. If it's a passive, if you just connect the two links and there's just, you throw one in the air and the other one is just, allowed to move with this motion. Okay. So this is just all of the dynamics that we need to describe any two bodies floating in the air. They're not fixed to anything. They're just floating in the air. They're just attached to each other by a joint. We have a bunch of equations now. How many equations do we have? We have 5 equations that describe what I just mentioned now. So to describe the motion of this, if you really want to describe it, which means mathematically model this system, and if you want to simulate it, you can do it, you need 5 equations. First, you need the dynamic equation of the parent rigid body, given by the Euler-Poincare equation. You need another dynamic equation of the child body, given by another Euler-Poincare equation. And inside of here, there are 3 equations that we just discussed that correspond to the joint. What the joint does in here is that it constrains the twists and the Q dot to be satisfying this equation. And it constrains also the wrenches and the torque to satisfy these 2 equations. So we have 3 equations, 3 constrained equations, and 2 differential equations. Does anyone know what the 5 equations together are called? They're called differential algebraic equations, DAEs. Who heard this term before? Okay. So differential algebraic equations is simply differential equations plus algebraic equations. These are the algebraic equations. You see, we don't have any differentiation here. The Q dot is actually not a differentiation. It's just the name of the variable. Okay? Just like the twist, it's the name of the variable. It's not the dot, of anything. We don't need to integrate here or differentiate. But here you see I have a differential equation of V dot. I have the time derivative of V, okay, and this is a function of V itself. So this is a differential equation in VC, and this is a differential equation in VP, while these 3 are just constraints on all of these 6 variables together. ODE, this one alone is called an ODE. So when we talked about the Euler-Poincare equation, it's just an ODE, it's an ordinary differential equation. While these 2 together, along with the constraints, they are collectively called the differential algebraic equation, a set of differential algebraic equations. Okay.
Subjected to these constraints?
Exactly. So I have these 2 equations. You have 2 rigid bodies. Each one of them is moving, is floating in space, and they're constrained by these 3 equations.
So we can't solve with these 2 equations, for example.
Of course not. No, you have to solve all of the 5 together. Exactly. You cannot solve. It's very easy. How can you integrate this equation without knowing the wrench?
The integrator itself, I can't take it, the constraints inside the integrator itself.
So now we're going to go into the simulation stuff. That's actually why I put this. So that's completely, we don't have any time to go into the details of this, but that's a whole course on its own. Okay, how do we actually build the simulation environment? So these 5 equations I just showed you, which is in this very simple example, you can generalize them to any multi-body system. And this differential algebraic equation is just a taste of the whole idea of what's beyond Simscape. If you ever use Simulink Simscape, then you're actually solving equations of this type. If you ever use Gazebo itself is just a software that is just, it's a combination of other packages the packages behind it is actually responsible for doing this integration in these equations is actually called you choose actually either ODE or Bullet or Dart. That's the name of the packages, the software packages that do it. And they call them inside of Gazebo they call the physics engine. It's not an engine, and it's it's a very bad word, but it's just computer scientists, they just use this terminology. Unity, okay. If you go to Unity, you're gonna find there's another set of equations. Okay. In the end, you have always these equations. Every software is just a smarter way or a different way, smarter or not, how will you solve these equations numerically. So you go from the mathematical differential algebraic equation into the discrete equation that you can solve on the computer. Okay. And that's actually a specialization by its own. So people, for example, if you really want to do stuff there, you need to be specialized in what's known as scientific computing. Okay? Machine learning and AI, there's actually part of scientific computing. It came from there. Okay? So again, the 5 equations that correspond to this simple parent-child system connected by one joint are 2 differential equations corresponding to the 2 rigid bodies that you have, and 3 constraints, one corresponding to the fact that you have that the velocity are related to each other, the velocity of the child and q dot and the velocity of the parent, they are related to each other by this equation, and the fact that you have Newton's third law, and the fact that you have a constraint here, that when you have this idea of the allowable spaces that you're allowed to move in, and there are some other spaces you're not allowed to move. So that's actually this third equation. All 3, the whole story of what I've been talking about for the last hour.
Is allowing some direction, forbidding other direction.
It's all of it at once. It's all of the equations at once. This is the general equations. How it happens, it's just you need to start from some initial condition and see what happens afterwards. That's exactly the solution of the differential equation. That's something else. That's exactly what you do with the software. You start from some initial condition. For example, you start by some velocity for this, and you leave this, for example, velocity 0. So you throw it in the air, and you find, for example, you can imagine, for example, that this link will start to rotate, and the other one will start to rotate around each other, and so on and so on. You're thinking about the solution to the differential equation, but that's the differential equation themselves that they satisfy.
These constraints only for these 2 links, it's not generalized.
What do you mean by not generalized? So now let's see whether this is generalizable or not. Yes, Aisha.
Then we have limits to how we can move even within the screw axis.
Yes.
Minus 80 to minus 180 to 180.
That's right.
Also presented in the equation.
No, here it's allowed, free motion. That's when you go to the simulation, you need to say that, for example, Q, has some limits, and Q dot has some limits, and so on and so forth. You start to put limits on the joints themselves, and in this way, you're actually going to be, and the way actually to solve this, properly speaking, you need to actually solve an optimization problem. And there you can put some quality or inequality constraints, and this is actually how some of the softwares they do it.
Sorry, we can put these constraints while we are designing the robot itself, when modeling the robot. When we import these files into, let's say, the Simulink or some other software, do they also have that information, or we need to define that?
That's an implementation issue. I don't know. That's a pure software issue. If you define them in one software, are they transferable or not? Completely no idea. Okay. Hopefully next time I'll show you what is the standard way of how we actually incorporate all of this information and how they do it, for example, in the simulation software that you're going to be using for the project. Okay. You need to do these 5 for every pair. And that's where we're going now. So the first thing that we need to add here to start talking about in extending it is just adding external wrenches. Okay. If I have an external wrench on the parent and an external wrench on the child, how does the equation change? Very easy. The constraints, they don't change at all. I just want to have extra wrench here in the Euler-Poincare and another external wrench here on the Euler-Poincare. Easy. It's very trivial. Now, how can this For example, now let me show you exactly how this looks like if you have a two-link robot arm, for example. So if I have a two-link robot arm, so I have the link dynamics of link number 2, and there's a joint connecting it to link number 1. Inside of this joint is just the constraints. There are 3 constraints. And now I have here another joint connecting it to what's supposed to be like the parent. But the parent itself doesn't have any dynamics. So the 0, which is the parent of the 1 frame, doesn't have any dynamics. Why? It's a fixed base manipulator, exactly. Which means that in the end, I just have here the twist of 0 with respect to S expressed in 0 is equal to 0, just 6 numbers of 0. Why? Because actually S frame and the 0 frame are the same frame. They're just, no relatives between them. They're just fixed. They are the same thing. So in the end, this is how the equations look like, how you can make a 2-link robot arm. Can you extend this to an N-link robot arm? Yes, of course, you can do. How many equations do we have here? Now count them that you need to program. I have here 1 equation, and here another equation. And here I have 3 constraints and 3 constraints. I have 1, 2, 3 equations here and 3 equations here. I have 8 equations. Now, each one of these equations, if you remember, is actually a column. For example, the Euler-Poincare equation, what was the dimension of the twist? It was 6, which means if you look at the Euler-Poincare equation, it's actually 6 differential equations coupled together. 1 in the rotational part of the X, 1 in the rotational part in the Y, 1 in the rotational part in the Z, 1 in the translational part in the X, 1 in the translational part in the Y, 1 in the translational part in the Z, and so on. So when I say here 1 equation, I mean in the terms of the twist. But if you're doing it, the old-fashioned way, and you're splitting rotation and translation, and you're using coordinates and X and Y and Z, you have here 6, you have here 6, you have here, I don't know how to count that. It's too much for me. Okay. You see now the benefit of working with the generalized coordinates. Everything becomes, doable. Okay? You can really extend and work on complicated stuff. Hopefully you're convinced by now. Okay. Not I don't know what convinces you. Okay. So this is generalizable to N rigid bodies. Now the last part of the lecture and of this topic, and it's the most important one. And it's very heavy in terms of the math, but once you sit down, after you eat and drink well, okay, and your body flourishes, you need to look at it at your own pace, inshallah, and you're gonna have the homework to play around with this and to really convince yourself that that's the case. What I just told you about this differential algebraic equation is very powerful, extensible, to a lot of situations. You can do even more stuff than just parallel than just serial linkages. You can do really a lot of stuff with it. You can do it in software. That's actually how software works. When we start to do control, you're usually representing a system like this is too much for control. Okay, we don't work actually with differential algebraic equations to do control. What in all of your studies, what's the starting point of doing control? Transfer function, you can't do anything. So transfer function is like, no, there's no transfer function is only for single input, single output, linear time invariant systems. These are non-linear. I won't go there. Okay. What's it called? State space. What state space something we're gonna look at if you didn't take it yet. But what's the state space equation? What type?
ODE.
First order ODE, exactly. It's a first order non-linear ODE. Okay, a system of ODEs exactly coupled together. So you see here we have differential algebraic equations. So all of the stuff that you learn about control, we cannot implement it to it, okay? Unless you learn how to do modeling. You learn how to do control for these systems. Some people are doing research in that area if you're interested. But what we want to do now is that we're able, because actually that's applicable for fixed base manipulators, even also for floating base manipulators. We can take this differential algebraic equation and we can reduce it into an equation that only depends on the Q's, the Q dots, and the tau. So you see here, we have all of these constrained wrenches from the body acting on the child, from the parent acting on the child, and the child acting on the parent. We have all of these twists. In the end, we can just eliminate all of the equation that you see on the top here, along with the constraints, and get in the end an equation that will take as an input tau1, tau2, and give you as an output q1 dot and q2 dot. And this equation inside of it will be a function of q dot, okay, and it will be a second order differential equation. That's the plan. Okay, so you're going to go from a differential algebraic equation to an ordinary differential equation. Yes.
Can we like reduce them down to first order differential equation?
Yes, you can. It's very easy to go from the second order to the first order. We're going to be doing that after the midterm, inshallah, to actually start doing the control. Yes, it's very easy to do it. Yeah.
Such heavy equations.
Yes.
We can represent everything in the equation form and then still apply the controller. So why do we need to bring it down?
What I'm talking, so that's a very good question. So when I said that when you need to do control, you need to have the ODEs. Okay, but what you're saying is that when I come to the simulation, I actually can apply the equation of the controller on the DAEs. What I'm talking about is the derivation of the controller set, the design part. When you want to design a controller, for example, use Lyapunov analysis, or whatever your favorite method is, you actually need to your starting point is the state space, which is a first order ODE, and thus, okay, this is what we need to do. Okay. So now this is the climax of the course. Okay, it's really the hardest part. Before the midterm, that's the hardest part that you're going to see everything coming together. But it's a recursive. Okay, so you're going to see there's a lot of repetitive. Okay, it's just that you do it from I equal to 1 to I equal to n. So it's just a lot just to take. Okay, so you need to really sit down and look at it step by step. I'll try to hopefully I try to to do it in the time that we have. The way we're going to be doing this reduction to go from the differential algebraic equation to the ordinary differential equation is actually known in the robotics literature by the recursive Newton-Euler algorithm. It's short for RNEA. Okay? It's an algorithm, it's a recursive algorithm that will exploit that actually, in fact, that you have a kinematic tree. What do you mean by a kinematic tree is that you have link 0 connected to link 1 by one joint. And then you have link 1 connecting to link 2 by another joint, and so on and so forth. You have a tree structure. You don't have any loops. Where do you find these loops? Does anyone remember what kind of robot does have this loops? The parallel robot, exactly. So parallel robots would have these loops. Here you have a kinematic tree structure. There you have a kinematic graph. So it doesn't work. You need more advanced tools. Okay. So, but if you want to use this stuff, you need to stick to the kinematic trees. So the algorithm starts by following. If you realize here that actually how the equations are connected, you see there is actually like some sort of order that you can move in. For example, you see that the V is related, so the V of the ith link is related to the V of the I minus 1 link. So the child is related to the parent. And I have here the Q dot, how it enters. This equation is the V, and I can simply derive it. Okay, I can take the time differentiation of it. Okay, if you differentiate this term, you get add multiplied by V dot plus the time derivative of the adjoint multiplied by the V. You all remember how the closed form of expression of the add looks like? We have a closed form. We can write it. I'll just leave it by the add dot. Okay. And if you want, you can expand it. And I have here this S was constant, or was it Q dependent or time dependent? Was a constant. So when I differentiate this term, I only get S multiplied by Q dot. So you see, I have a closed form expression for the V of the ith link, and I have a closed form expression for the V of the I dot. Okay, so you see I have closed form for V, closed form for V dot. And that's for the ith link. The only piece of information I need to know here is actually the Q's. So you see I can take the Q's starting from Q1, okay, and the initial velocity of the base, which is 0. So I can start from Q1, I can know V1. And then afterwards I have V1 now. I can plug it in and I can get V2 as a function of V1 and Q2 dot, and so on and so forth. So I can go in a forward pass from Q1 dot up till the V of the nth link. So I can go in the forward pass. And in the backward pass, I can use this equation of the Euler-Poincare, but in a reversed order. You remember how we always look like? We always have it as I multiplied by V dot is equal to all of the stuff on the right-hand side. But if we can re-parameterize it such that we have that the constraint range is actually the output of this equation. You see on the right-hand side, I have the V dot, which I calculated in the forward pass. This is a function of V, which also I calculated in the forward pass. And this is a function of the range of the next link, exactly, of the child. So you see why this is why we need to start with the backward pass. Because if I start here by the last link, I don't have anything connected to it. So I have this to be a 0. So I can calculate the V of the last link, and then I can plug it in back, going back in this direction. So you see how it goes? If you follow the arrows here, okay, I can just plug in I can assume I have the Q1 dot. I can go in this direction, and then I can go back, and I can calculate in the end the tau from this equation by just multiplying to all of these ranges the S transpose. Okay, it's too much to comprehend at the moment, but you see this is just, you know, if you watch this video, you know, 10 times, inshallah, you'll understand. Yes, velocity is forward, and the wrench is back.
Take it from forward velocity.
All of the V's that we calculated, you see? And we also need the wrench of the next link. And that's why you need to start from the last one, because there is nothing after it.
So also in the backward or the next step, if each part depends on the progress.
Exactly. You see, so there's a recursive form. Okay, and this is very important. You know, if you do it this way, it's actually, by the way, it's very easy. Last year I did it actually in the lecture. Okay, we did it for a 2 link. We had 1 hour 15 minutes to actually do it for 2 links. Okay, but it's easy. So I'll give you the video if you want to watch it. But in the end, you can just trust me. Okay, this is really how it works. You have only 2 equations. And if you combine it with this one, in the end, you're just going to reach and then n equations. For the 2-link robot arm, you're going to get 2. For the n-link robot arm, you're going to get n equations.
Talk about the first constraint, the first equation in the constraint. That was like this, the first one.
Yes.
This is a generalized one. Instead of having 2, one for this d and one for this d, we have only this as a generalized form of the
Yes.
equation.
Yeah.
So this is one.
Okay.
And the other 2 are the 2 in the next slide.
That's right.
3 equations instead of 8 equations for the 2.
No, but okay, no, wait. What you need to do here is that you need to substitute. You calculate this for all of the links sequentially. So in the end, for example, let's say that you have 2 links, then you're going to have 2 equations here, 2 equations here. So that's 4. And then you come here, how many equations do you have here? You have also 2. But when you plug these 4 into these 2, okay? Okay, you'll have to do it by yourself, okay? You have to do it really by yourself to see what happens, okay? But the bottom line is that when you apply the tau in the end, when you multiply the S transpose to all of these 2 equations, in the end, they will be combined, okay, into one equation in terms of the tau. One equation for tau 1 and another equation for tau 2. So in the end, you're going to reach n equations. That's exactly the homework, inshallah, for the 2-link robot arm, okay? So that's exactly why you need to do it by yourself. So
so that we have numbers and we can actually.
no, you're gonna actually do it by like this. No, just like this with equations. You just write this 1, 2, and 3, and you plug it in, and you see really with your eyes how it does look like. In terms of just algebraic equation, yes.
Finish this backward and then get to the top.
Exactly. Yeah, exactly. 3 steps, exactly. You calculate these 2 in the forward pass, and in the backward you do with this, okay, and then you get this. But by the way, this you can get from, you know, once I calculate this, I can get this. So these actually are another, you know, or just once you can combine this. Just like when these, I can do them at the same time. I can do this and then this directly. I can do this and then this directly. You see?
So these 3 steps to get the torques for each joint.
To get a function of the torques and the Qs. So in the end, what you're left with is that you've eliminated all of the wrenches, and you've also eliminated here all of the V and the V dots. What you're left with is only a function of taus and Qs and Q dots and Q double dots.
To get or they none.
No, that's the equation in the end. Equation from taus to Q dot double dot. So from tau to Q double dot is this picture. You see, I have an equation
from these three steps.
Yeah.
What about the Q and the Q?
They're left as a differential equation. You have them as an unknown, but now you're left with the differential equation of tau and Q dot, Q double dot. Now you can solve this differential equation. Now you need to solve it still.
Executions to get these three.
N. I get to get n. These are n ordered differential equations. Okay. I can show it to you. Okay, if you just give me the time. Okay, I can show you how you can derive it very easily. There's actually a very, very elegant way. In 10 minutes, inshallah. Okay, we'll do it. Okay.
The derivation of V.
This one?
Yes. Just can you explain how we get Q double dot?
This one.
Yeah.
Differentiation of this term is these two. Differentiation of that term is differentiation of this multiplied by Q dot plus this multiplied by Q double dot. Differentiation of this is equal to? It's a constant.
0.
You're left with this term. Clear? Okay. So, okay, buckle your seatbelts, okay? So this is what we're going to be doing. You see this recursive equation? You need to convince yourself that it can be actually written as this one equation. Take a look at it. If we have now the VI, I have V1, V2 up to Vn, right? I can put them all together in the 6n vector. It's 6 multiplied by n. Okay, so for example, if I have two rigid bodies, this is a 12 vector because I have 6 for the first one and afterwards 6 for the second one. So I just stack them all on top of each other. So that's all of the twists. And now this adjoint, okay, I can make it. You see, it's multiplied by the twist. So I have here a function twist, and this is a twist. But there's it's not the same twist. It's like exactly the parent one. So you see, that's exactly what you have in this equation. I can define this A. I can combine all of this recursive part into this A matrix, such that when I stack all of these, they are given by V is equal to A of Q multiplied by V. You can test it very quickly like this. If I have V1, which is the first row here, I have a joint of 0 with respect to 1 multiplied by the V of 0 with respect to S expressed in 0. What is this term? 0. So I don't have any term in the first equation. If I have this to V2, which is the second row here, I have add of 1 with respect to 2, and this is V1 with respect to S expressed in 1. You see here, this is multiplied by the first column, and the first one here is V1, 1S. Okay, so you just need to expand this term. Okay, and you see actually these two, they are exactly the same if you stack everything on top of each other. This term is also easy because this term for the ith twist, I multiply by the ith Q. So in the end, you see I have a block diagonal matrix where every block here is simply the twist Si. And the dimensions here, they are written, and you need to get your head around them just to convince yourself that they are true. So this equation, if I write them for I equal to 1 up to I equal to n and put them on top of each other, I can write them as this equation. Okay, convinced? At least, I don't know if you're not convinced with the math, but at least is it clear what's doing? We're writing in a compact form, exactly. Just writing in a compact form, yes. We're not adding them. There's a map here that will eat this one and will split 6n that you can add it to each other. And this is 6n by 6n, which means you can multiply by this, you can get 6n. This is the dimensions they match. Clear?
Chain robot?
Yes. Assuming you have an open chain. 1, 3, exactly. Yes, exactly. If you have, at some point, you have multiple links at the same stuff, things that are a little bit, slightly different, but still you can do it. Okay, you start to have, multiple rows. Okay, multiple columns in the same row, populated. That's the first thing. Can we write this equation, which is for the V dots, as this one? Exactly the same. There's nothing new. We did not introduce anything new, except for all of the Q dots. If you stack them together, we're going to call this Q dot, double dot. If you stack all of the V dots together, you're going to get this as V dot. And here I had the A. Initially, I had the add and the differential of the add. So here I'm going to call this A, and I'm going to call this A dot. Okay? So A dot, we're going to leave it as an A dot. But if you want really to expand it and write it as differential, as a closed form expression, you need to go back. You remember to the fact that the d by dt of the add is equal to the small add multiplied by the and then so on. What you did in the homework. For the wrench, for this top equation, and for the twist, I can write them as these two equations by doing the following. All of the wrenches, I can stack them on top of each other. Okay? All of the i's that were here, I put them in a block diagonal matrix of this form. And the tau, all of them, I put them in one big stacked vector. And we're left with this adjoint transpose. This adjoint transpose of V is actually a 6 by 6 matrix. If I also concatenate them in this way, I can make it out of it one big add V matrix. Which means that I can write these two as this. Okay? So what I did now is that I took all of these recursive equations and we just put them into these four set of equations. Make sense? Yeah. If you know how to do matrix manipulation, now you can easily follow from here. You see I have an equation which is V and V here. V dot and V dot. W and W here. What we're going to be doing is that we're going to be putting everything on the same side. We're going to get something like this. Make sense to you? So this was the V minus A of Q multiplied by V is actually identity. So this is a very big identity matrix. Okay, that I subtract from it the A of Q multiplied by the V, I get this expression. Make sense for everyone? What's the next step? We want to leave the V alone here and the V dot alone and the W alone. What do? Invert this term. You see how huge this matrix is? Okay. It has a very neat closed form expression for the inverse. So I minus A of Q, if you take the inverse of this huge matrix, it's actually equivalent to this 6n by 6n matrix. That in the end, it just has adjoints inside. So you can program it. Very easy to program. So I can take all of these expressions and I can rewrite them as this. Make sense? And then substitute. What do you substitute what with what? So you see I can take the V. So let's take this tau. Tau is equal to S transpose multiplied by W. This is the W. It's L transpose multiplied by I by V dot. So I have V dot here. I can plug it in this term. And I have here the V here twice. So I can plug in that term. That's exactly what we're going to do. And even here in the V dot, I also have a V, which I'm going to be plugging it with this term. So I plug this one in this and this. I take this one, I plug it here. And I take all of what comes out, I put it in this expression. Okay? It's ugly, but it's, you can spend one night on it, okay? Exactly. We will leave them as unknowns. You'll see in a bit, okay? So we have this expression, okay? What this ugly term is, what I just said. You just plug in everything. If you look at very carefully, I know you don't have the mental power to do it right now. You're going to see that there's an L multiplied by S that appears a lot. L times S, L times S. This is S transpose L transpose, which is actually the transpose of this LS, LS, S transpose L transpose. Let's introduce a new variable. Let's call it J instead of all of this LS. And let's rewrite this expression like this. What I'm going to do now is that I'm going to take this is a very special term because it's J transpose I, and there's a J multiplied by Q double dot. I want this term alone. And everything else, you see, I can multiply by Q dot. I'm going to introduce two matrices. One called M, one called C. And we'll get this equation in the end. Have you seen this equation before? If you did any robotics, you must have seen this equation. If you read any paper on robotics, this is the starting point. They say the equation of motion of a fixed base manipulator is given by this. It's actually missing a number of terms we're going to be working looking at them on Sunday, inshallah. But that's the equation. So what you see here is a differential equation. It's a second order differential equation that has tau as an input, and it's a function of q dot, and in the end I just have q double dot. So it's a second order differential equation in q with a tau as an input. What is this m? I can calculate it with this fancy expression. What is the c and the q? And the q dot is a very long expression that's given by this matrix. In the end, if you program it, you look at what you have here, you just have a matrix. Okay, you just have like a block in your favorite program as an equation that eats the tau, and in the end calculates from this expression the q double dot. I can integrate it once to get the q dot, integrate it again to get the q. I need the q and the q dot to have inside of this equation, and as an output I have the q dot here. So in the end, we've taken this huge differential algebraic equation, and we've just wrote it in a n by n, okay, or an n ordinary differential equations. Of course, they're nonlinear. They're highly coupled, so the m and the c. You don't expect this to be diagonal, okay? So this is highly coupled. But in the end, we've just done the differential equations of the robot.
So we assume it's linear differential.
No. The m is completely nonlinear. So this is nonlinear, a differential equation. It's a nonlinear, ordinary, second order differential equation. Yes.
This is the same m that we mentioned in the beginning.
Absolutely. How to show that next time, inshallah. So again, so we derived an m, okay, earlier today, that had a summation of some j's and some i's. They are actually inside of here. I just need to convince it to you. Okay, you actually have all the tools. If you go back to here and just write it down, you'll see that it is true that actually these two terms actually are the same. So actually, I either put in the homework or I show it to you next time. I haven't decided. Okay. Let's stop here. Okay. So if you want, I can take the questions after. But in case someone wants to leave. Okay?